Hello and welcome to this video on center of mass.
Imagine you have two books sitting on a shelf. We can talk about each of these objects individually, or we can talk about them collectively. We're going to do both for sake of comparison. We'll start by talking about book one. What's touching book one?
What are the objects it's interacting with? What are the forces acting upon it?
Well, we see right away, we see book two. Book two is touching book one. And see it touch. Other than that, the air. The air is touching it. We can talk about that. But is there anything else really touching book one? I'm not touching it. You're not touching it. There's no shelf. There's no surface. We haven't talked about the wall, but we're going to assume it doesn't for the sake of this example. The only other thing we have to talk about is gravity. When we talk about what forces might be interacting on an object, they fall into two categories. Things that directly touch, which are called contact forces, and then things that work at a distance. We call those field forces. The only one we're going to focus on right now for field forces is gravity. We'll add more later. But whenever you're talking or making a list of all the forces that might be interacting with an object, start with what's touching. Anything that's touching probably is providing a force of some kind. Then talk about gravity, add it on if you're somewhere where you have gravity, which is anywhere that things fall. If that shelf wasn't there, would this fall? Yes or no? If yes, gravity. Same thing with like a marker or anything else. If you're on the Earth, gravity is probably a factor. What about book two?
Can you identify all the forces acting on book 2? Give it a try on your own and check back after the pause.
What's touching book two? Well, we have book one. We have the air again. We have the shelf. And we have gravity. Now, if I were to suddenly have the shelf collapse, if the shelf broke underneath these two books, bad shelf, would these two books fall separately or would they fall together? We've seen this. The demonstration with the paper on top of the book. The two of them will fall in unison. They'll fall at the same time. They'll fall in such a way that there's no practical difference between them. They fall, if you'd prefer, as a system. So let's talk about the forces acting on the system. Okay? So instead of treating the two books as separate, we treat them as one singular object, one combined object. And what's acting on them together?
To the answer to that question, what I want you to do is draw the little web diagrams that we were doing in the previous video, and then draw a box around the system of the two books. Check back after the pause.
So if you went through and did this, you'd get that the system is book one and book two, and as we circle it, we find that this force right here between book one and book two is largely irrelevant for our system, as is this force between air and gravity, and air and gravity and the shelf, and even this force that I forgot to draw in between air and the shelf. Those aren't relevant to what we're talking about. They aren't relevant to our system. The ones that do matter, gravity on book one, gravity on book two, air on book one, air on book two, and the shelf. These are the forces that are going to be acting on our system, and we'll even be able to eliminate some of those down the road. But for right now, that is the ones acting on our system.
Let's talk about this system here, the dog and
One of
person
the nice things about defining a system is once you've defined a system and it's truly acting as a single object. If the dog and the person are moving at the same pace, they're all interacting together. In this case, the dog's doing the driving, so to speak. You can treat them as a single object, and as such, your math gets a lot easier. Instead of having to measure everything that acts on the person, the dog, the leash, you can treat everything as acting on the system as a whole. This allows for a few mathematical shortcuts. To make this a little easier to understand, let's talk about the books again. Instead of us treating this as two objects with varying sizes and masses, what we do in physics is instead treat it as a single object. And instead of saying, these two get pulled unevenly or differently, we say that it acts on the center of mass. What's the center of mass? Well, the center of mass
is a point where if I averaged all the masses of an object together, they'd add up to 0. Everything would equally balance. Or another way to say this is,
we're to take an object, it's the point where if you held it on a pinky, it would balance. And if you push on that, it pushes on the entire object as a whole. Now, I can't quite do it here, but every object on the planet has one of these balance points. Some of them, say like a stapler, are harder to find. Some of them are fairly easy. Meter stick is fairly easy. It's right there in the middle. And if there wasn't any tape there, it'd be perfect. This balance point, the center of mass. Now, this is a simplification that makes our life easier. But whenever we talk about a system or an object and a force acting on it or interaction on it or it falling, we treat it as if the center of mass
is where those forces are acting at.
A common way to talk about this is imagine two blocks.
The blocks have equal mass, they're the same mass.
Block A, block B. The center of mass is exactly halfway between them, because it is the equal point between them. If block A is going to start falling, block B is going to start falling. If block A moves to the left, block B is going to move to the left if they're truly a single object, or they're connected, to be treated as a single object. And the center of mass is where we treat all interactions happening. What this allows us to do is it goes, okay, instead of having to do the kinematics equation for this one, the delta x equals v naught t plus 1/2 a t squared for this one, and then do it again over here. And then looking at those results separately and talking about it, we can go, okay, let's do it just for the center of mass and simplify our work. In short, in essence, if you can find the center of mass, you can simplify your math down to one set of interactions acting at the center of mass. With that said, thanks for watching.